Hello, everyone. This is Yuen, and today I'm going to introduce our paper, Causally Testing Gender Bias in LLMs, a case study on occupational bias. This is a joint work between Yuen, Vetha, Justus, Rada, and Zhijing. The motivation of this work is first, the gender bias that's encoded in pre-trained language models. For example, when the machine learning researcher asks their ChatGPT to draw the picture depicting their lifestyle, we see that most of the time it draws a male figure, regardless of the gender of this user. And this happens to both myself and many of my colleagues. This is not surprising, as the training data of large language models also encode the existing gender bias in this society. For example, in books, there are twice as many male expression tokens than female ones. And this is reflected in a generated text of language models. We see that they generated twice as many language relevant to male than females. There are many existing gender bias benchmarks that tries to quantify such biases. However, one of the main limitations they have is the confounding issue. For example, consider this example from stereo set. We see this gray area, the template says, she was confident in blank, but afraid to face the boys club in the industry. So in this template, the model is supposed to make a prediction about what the blank should be, whether it should be herself, himself, themselves. However, if we look at the templates, it already starts with the word she. So the only natural words that fits in this blank would be herself. And in this case, if we look at the causal graph on the right, we do not know whether this female prediction is caused by the stereotypes such as confident and afraid, or it's solely caused by these templates that uses the word she. And in this case, the templates and stereotypes are confounded by this confounder called the writer's intention. So in this case of confounding, we have the conditional probability not equal to the interventional probability. So the conditional probability we measure is not the causal effect of this stereotypes on the predicted gender. Another issue with existing benchmarks is verbalization noise. For example, consider this example from stereo set. The anti-stereotypical sentence says he was an excellent cook. And this has a relatively lower probability than the stereotypical sentence. However, if we simply add one word also, that does not change the sentence or meaning of the sentence, but we see that the relation between these two probability flipped. Now it's more likely that the model will predict the anti-stereotypical sentence. Let's look at another example in stereo set. So in this context, we have stereotypical prediction pranks and anti-stereotypical prediction fashion. And we see that the model is more likely to predict the stereotypical one than fashion. However, if we simply paraphrase pranks with jokes, then this anti-stereotypical prediction becomes more likely, which also flipped the relation between these two probability. So having seen the limitation of existing benchmarks, we propose the following framework. We first choose a template, such as I have a friend who is someone, a job, and blank. So this job will be filled in by some occupations that we later will discuss how we choose them. And the gender is simply a gender expression such as he, she, they. Our dataset is called OccuGender, where we loop over all the templates, occupation, and gender combination to ensure their independence. For the occupations, we chose from the US Bureau of Labor Statistics, where we find the 20 jobs with highest male ratio and 20 jobs with highest female ratio, and use them as our stereotype. For the templates, we prompt ChatGPT-4 to generate a diverse set of templates that fit in our context. And some additional characteristic of OccuGender is we test both explicit and implicit bias. For explicit bias, we mean those that directly states a firefighter is a male. And for implicit bias, it would be ones that infer the gender without explicitly saying it. For example, if it says the word firefighter, then it directly starts using the pronoun he. Then it's making an implicit assumption that this firefighter must be a male. We ensure small prediction space in that we ask the language model to predict the gender instead of the stereotypes, as there are much more ways of verbalizing or paraphrasing one stereotype than a gender. And lastly, we include non-binary genders for the inclusion purpose. So our goal is to find this causal estimate. What's the probability of this model predicting a certain gender if the stereotype is set to some stereotype S? This is our causal effect. By definition of conditional probability, we can expand this expression into a summation sum that's summed over all the possible templates. And now if we look at this causal graph, we see that now because we cut off the independence between the confounding, if any possible confounding between templates and stereotypes, as we choose them independently, this due notation reduces to simply the conditional probability. And next, because template is independent from stereotypes, we see that this conditional probability again reduces to the marginal probability. And because we cannot possibly test all the templates, we choose a diverse set to approximate this space. And we average over all the templates that we test, which is an approximation of the causal effect. So we tested our OccuGender on 10 state-of-the-art language models, including Llama 2, Llama 3, Mistral, Gamma, and Gamma 2. The summary of our results is, yes, these LLMs do reflect occupational gender bias within human society. Here we look at a snippet of our experimental table. So we report explicit bias and implicit bias separately. And for each type of biases, we also separate the male-dominated jobs and female-dominated jobs. And each of the MFD corresponds to the male expression, female expression, and diverse expression. So for example, in this column, we see that for male-dominated jobs, it's very likely that a language model or this language model will predict male with almost 100% probability. And for this implicit bias, it's a little bit better, but still very extreme. And here's the completed table. Below, we will discuss some of the observations we have. The first being that the language models are more biased for male-dominated job, in that when we consider the columns correspond to the male-dominated jobs, the language models predicts close to 100% male, and it doesn't really produce that much female expression or non-binary expression, and same for male-dominated implicit bias. And similarly for implicit bias in male-dominated jobs. And the second is instruction tuning amplifies biases in llamas and gammas. So for each group, to each two rows, we group them by their base models. So on the top, we have the base version of llama 2.7b, for example. And on the bottom, we have the instruction tuned version. We see that for the instruction tuned version, the probability of predicting female jumped from 54 to 73, making this even more unbalanced. And similar pattern is also observed in male prediction for male-dominated jobs. And also, this also occurs in the implicit bias. And lastly, we observe that base models mostly recognize non-binary genders, in that makes close to zero probability in predicting non-binary gender for explicit bias. And even though it's a bit better, but it's still consistently less than 10% for implicit bias. So to summarize, we point out the following interesting future works. The first is bias mitigation via prompting. As the size of language models gets larger, it gets more computationally expensive to fine-tune them. So it remains an interesting direction on how to develop prompting strategies for bias mitigation. And the causal framework we introduce here, although we only apply it to occupational gender bias, it's generally applicable to other type of biases. So what are other social biases in LLMs we need to address is another potential direction. And we summarize our contribution. First, we propose a new causal framework for measuring biases in language models. Building upon this framework, we introduce a benchmark, RQGender, for testing occupational gender bias in LLMs. And we apply this RQGender dataset to test 10 open source state-of-the-art LLMs on the biases they exhibit. We encourage you to check out our paper here or scan this QR code. Thank you for your attention.